Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue to talk about Bayesian regression. And here we'll look at the implementation in Python. So, before we do that, we'll look at some plots that compare the coefficients between the Bayesian Ridge, then the automatic relevance determination, and ordinary least squares. So, just a quick recap. This is the equation that we have discussed in previous video, where the the Gaussian normal distribution for y, p of for y given given the input x, parameters w, and the hyperparameter alpha is denoted like this. And when we are looking at ridge regression, we have the normal distribution which has a zero mean as shown here, and that is what is used to calculate the priors. So the priors are used to inform the uh, calculation of current weights using along with the data. And again, for automatic relevance determination, the prior is determined by this Gaussian function, which is again at a zero mean. Now, the difference between the Bayesian Ridge regression and the automatic relevance determination is that in this case, in ARD, each of the parameter W has its own standard deviation, and that's the difference between those two methods. Now, this is a plot that shows the fit for both the Bayesian Ridge and the automatic relevance determination. And the original data, that's the ground truth, here is by the shown by the yellow line that's hiding behind these two curves. And then the orange line is the ARD, and the blue line is the Bayesian Ridge regression. And as you can see, they do a pretty good job for fit up to this point. And the reason why these points are away from the actual data curve, orange curve here, that's because these values from the test set are outside the range of on what the model was trained on, and that's why they are out there. These vertical lines are the error bars, and thus we can see that for any given feature x, we are able to predict the feature y for using the Bayesian models. Here is another example where we have four plots on the left side, and there is the overlay plot of those four plots on the right hand side, and given by the labels here. Now, a couple of points to note in these plots is that if we look at just the coefficients on the x-axis has the features and y-axis. So this for this particular fit, there were 100 different features based on the polynomial that we saw earlier, and then each of those features there would be weights assigned to it. And as we can see, for the ordinary least squares, the number of the variation in the in the weights of the parameter weights of the features is much higher. As you can see, it's unstable, the line goes up and down a lot. And as compared to that, in Bayesian Ridge, that is more stabilized. The fluctuations are much less in case of the Bayesian Ridge, as you can see. And in the automatic relevance determination, there should be n here. We can see that the values for the coefficients are much closer to zero as compared to the Bayesian Ridge, and certainly more stable than the ordinary least squares. And here on the right hand side, we have the overlay where we can see the that the OLS is much more unstable, and as we go down to the ARD, the stability is increased much more. On this plot, we can see on the left hand side is the distribution of the coefficients for Bayesian Ridge, and we can see it's more like a normal distribution, and it is nice spread out as compared to that. In the middle plot, in the automatic relevance determination, we can see that most of the coefficients are 0, and therefore there is a sharp peak at 0, and hence the histogram is much narrower as compared to the Bayesian ridge. And here we can see that in the overlay plot as well, where the orange part is for the ARD and the blue histogram in the background is for the Bayesian ridge. Now let's get into Jupyter Notebook and see how we can code these. Here I've imported a couple of libraries, NumPy, Matplotlib, and I imported these libraries from Scikit-learn, and these are the versions that I'm using. So let me run this again. Okay. And for data, we are going to use two different types of data sets. So we'll create them as we go. The first one, we will use the diabetes data set. So data is equal to data sets dot load underscore diabetes, and here we'll create the x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split data dot data and data dot target. So that's the data we'll try first, and then after that we'll use another data set. We'll create that one later. So first we'll look at fitting a linear regression as and see how that works. For linear regression, we'll create a variable called OLS. OLS is equal to linear underscore model dot linear regression, and then we can do OLS dot fit fit to the X train and Y train, and after that we can calculate the predicted value for Y using the test set. So OLS dot predict, and this would be on the X underscore test, and using both of these then we can calculate the score. So OLS underscore score is equal to matrix dot mean underscore squared underscore error, and here we use the y underscore test OLS underscore predict that we calculated above. And now we can go ahead and print the coefficients. So coefficients for this, and here we can specify the coefficients OLS.coef underscore, round them up to 2 decimal places, and then on the we'll skip a line there, and then we'll print the score. So score, which is the MAC actually. So this is the MAC, and that the value for that score is going to be in the variable OLS underscore score. So these are the variables we have, and that's the MAC that we get. Just to recap, the MAC, the lower the MAC, the better it is. Now now let's go ahead and fit the Bayesian Ridge, the Bayesian Ridge, and see how that model fits to this data. We are using all the default settings without any changes to the parameters. So this is Bayesian Ridge, and I'm going to change the variable that I'm using here to BYR. So just going to copy all the BYRs in place of all the OLS that I've written here. So that should do it. All the BLS is copied, and for Bayesian Ridge we get these values. The MSC is a bit higher than what we have for Ridge regression, but then one point we can see that the coefficients tend to be a little smaller. We'll plot them and look at them visually how they look. So that is to say that introducing regularization in Bayesian Ridge, we are stabilizing the coefficients. The last one we'll look at is the automatic relevance determination, ARD, and for this we'll use the variable ARD in all these cases. So ARD, and then we have ARD right here. And finally, we calculate the score again based on the predicted value for ARD. And we have the score right here. So these are the values for the automatic relevance determination and the coefficient. So the there's something probably we need to check. If we if we see that the numbers match up to all these decimal places with the earlier, there's definitely something wrong, and that's because here we did not change the model that we are using. So here we need to change this and put ARDRegression, and now we have these values. So a difference in compared to Bayesian Ridge, now we start seeing zeros for some of the weights that are the coefficients. So that's the difference between the Ridge and the ARD. We can now go ahead and plot these. So we'll create a simple plot, and we've seen similar plot in the on the slides before, but that was with a different example. Here we have very few parameters, but still we should be able to see the difference. So on the x-axis, we just have numbers for the coefficients, and then on the y-axis, we'll plot the coefficients, OLS dot coefficients, and then same thing we want to do for the rest of the other two, which is the BYR, that is for the Bayesian Ridge, and then we have the last one, ARD, that's for the automatic relevance determination. And here I'm just going to go ahead and add a line, a horizontal line, just to see where the zero is at and make it easier to visualize. So we'll create a dotted line there. Now if we look at the plots, we see that this the plot is not really convincing to show us that the coefficients are closer to zero in case of ARD as compared to the OLS. That's because we have very few coefficients there, and we can change that. So let's use another data set now. But this data set, the idea was to show you how this works. We have different coefficients going to zero. Now when we change the data set, so we'll create a random data set here for the X train, Y train, and similarly for the test. So this, let's call this data 2, and let's call this data 1. So we're done with the data 1. For data 2, we create x underscore train is equal to np.random number, and we'll create 100 rows, so 100 samples, and we have 100 features. So this would be similar to number of n number of samples and number of features. Okay, features. And similar to this, then we have the Y train, which is I'm going to add all the X train along for all the columns, so along axis 1, and to this I'm going to multiply these by some random numbers and just to add some noise in there. So 100, and then we have that for the train set, and we need to create a similar set for the test set. So here I'm going to change this to test, and we don't need 100, 50 samples would do it. So changing that to 50. Number of features has to stay the same, so that I'll leave that at 100. So when we run this, and now when we go ahead and run our models again, which are these, here we can see that Ridge has zeroed most of these coefficients, and so has the automatic relevance determination. Now this is an overlay plot, so to get a better look, we can look at them one by one as well. So here we see that this is the ordinary least squares, and on top of that, if we add the Bayesian Ridge, the coefficients are so small that we cannot see. I'll comment that line out. So this is for Bayesian Ridge, and then this is for automatic. These are even smaller than what we have for Bayesian Ridge, or they are bigger than that. So the values for the Bayesian Ridge have gone. They are too small to be seen on this particular plot, because most of them are very close to 0 in this example. So let's go ahead and plot all 3 of them together. So that's how the coefficient would look like when we plot them. Now, in addition to this plot, we can also go ahead and plot the histogram to look at the distribution of the coefficients or weights. So to do that, we'll plot plt.hist, and here we'll first go ahead and plot the coefficients for the OLS, and bins, number of bins, we'll set it to the length of the array that has the number of features. So bins is equal to number of features. When we plot that as plt.show, here we can see that's the distribution. Now on top of this, we can plot the Bayesian Ridge byr, and again change that there. So these, the color is equal to red, and the reason why we cannot see those lines on this plot is because it is too small. And when we remove that, this is, so it's in a very small range between minus 0.01 to plus 0.01, and whereas for OLS it's between minus say 30 to minus 60. So this BYR plot is right somewhere at the origin near 0. And in addition to that, we can also plot the values for the A automatic relevance determination, ARD, and maybe green color for those. Again, the we can see that most of the values are at 0, and that is seen here by the sharp peak. Whereas if we zoom in, so if we zoom in, we can see that the values for BYR are there, but they are much smaller in there, so we can see them in clearly. So that was it for this video, where we looked at the examples of how the coefficients for the Bayesian Ridge, a linear regression, and the automatic relevance determination compare. We also tried to compare the histograms of the coefficient to look at the spread, how much variation is there in that in the weights. And from the fit coefficients, we also saw that as compared to linear regression, the coefficients are much more stable, in that there is lesser variation in the values of the coefficients or values of the weights that are used for each of those features. I hope in this and past 2 videos you learned about how Bayesian regression works, how conditional probability is used, and how the what how important it is to determine the prior information for the parameters to calculate new values for those parameters, and that are the weights. So in the main takeaway message from these 3 videos on Bayes regression is that for Bayesian regression, when we start calculating the values for parameters, we start with prior unknown prior as in we start with values. In this case, they are drawn from a gamma distribution, and those are used to calculate a new set of values for the weights. and then the weights are updated with different iterations to get the final output. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.